In this video, I will present SafeguardGS, our effective pruning technique for 3D Gaussian splitting. Recent studies in the novel view synthesis task have shown promising improvements in generating novel view images. One of the most iconic work is 3D Gaussian splitting, which is commonly abbreviated as 3DGS. With a differential laser, 3DGS reconstructs 3D scenes using learnable 3D Gaussian primitives and achieves photorealistic rendering quality. While its performance is highly impressive, the explosive growth of 3D Gaussians during training has emerged as a major bottleneck in both training time and memory usage. Interestingly, although the number of Gaussians often exceeds 1 million, most of them are redundant and contribute little to rendering quality, as shown by the red curve in the graph. Even when nearly 60% of the Gaussians are pruned, the rendering quality remains almost unchanged. Based on this observation, several works have proposed their own pruning criteria to identify and remove redundant Gaussians. However, none of them provide an in-depth analysis of the characteristics of their pruning functions. Therefore, in this work, we aim to gain deeper insight into designing an effective pruning functions. First, we categorize pruning techniques into two major types. The first type is scene-level importance threshold-based pruning, or slit pruning. The second type is pixel-level importance length-based pruning, or blur pruning. The key difference lies in how the importance of each Gaussian is measured. In slit pruning, the importance score of a Gaussian is aggregated from sub-scores computed across intersecting camera rays. The aggregation can involve summation, multiplication, and other operations. Once the scores are computed, Gaussians with scores below a predefined threshold are removed. In contrast, blur pruning computes importance scores per ray and retains only the top K Gaussians for each ray. This top K selection is applied independently for every ray. We observe that these different pruning mechanisms lead to two important properties of blur pruning. In slit pruning, because importance scores are aggregated across multiple rays, Gaussians intersecting many rays may receive artificially high importance, even if they are not truly significant. Additionally, because pruning is applied globally, some rays may end up with no remaining Gaussians. In contrast, blur pruning mitigates these issues by operating on a per-ray basis. Our experiments show that blur pruning generally outperforms slit pruning. This graph illustrates PSNR response to the number of Gaussian primitives under different pruning settings, such as pruning ratio or top K selection. We observe that slit methods exhibit a steeper drop in quality when fewer primitives remain. Interestingly, blur pruning inherently prevents overly aggressive pruning. The most extreme case is top K equal 1, just before a sharp quality drop occurs. We refer to this natural boundary as a safeguard. It is clear that the quality of the pruned scene depends on the scoring function. We further explore effective scoring functions that maximize per Gaussian expressiveness. By revisiting the 3D rendering equation, we propose multiple candidate scoring functions by combining its factors, including Gaussian parameters and analytical values such as opacity and transmittance and color similarity to ground truth pixel. We conduct experiments to evaluate the pruning function candidates under various top K selections. Most scoring functions cluster in a high-performance group. Among them, scoring functions 4 and 36 perform the highest. We identify score function 36 as the most effective, as it consistently achieves higher per primitive expressiveness. For example, at top k equal 1, it outperforms score function 4 by 0.06, 10 over minus 5, and at top k equal 100, it outperforms by 0.03, 10 over minus 5. Based on this analysis, we propose an effective pruning technique, the SafeguardGS. It leverages blur pruning with score function 36, which incorporates color similarity and blending weight. To evaluate our method, we conduct experiments on 4 datasets and measure various metrics, including reconstruction quality, training speed, and per primitive expressiveness. For a fair comparison, we implement baseline pruning methods within the vanilla 3D.js training pipeline. Pruning is applied once at 20k iterations out of 30k. We tune our method to achieve a similar compression ratio of approximately 90%. We adopt pruning functions from like Gaussian, min-splitting, lot spread, and efficient.js as baselines. The results show that SafeguardGS more effectively identifies important Gaussians. For example, on the MIMNURF 360 dataset, like Gaussian, min-splitting, and lot split achieve under 27 dB PSNR, despite retaining more Gaussians. Compared to efficient.js, our method achieves an additional 0.06, 10 over minus 5 improvement in per primitive expressiveness. We also observed reduced training time and faster rendering compared to the original 3D.js. We further apply SafeguardGS to other state-of-the-art pruning pipelines by replacing their pruning modules with ours. The results demonstrate improved pruning effectiveness. For example, on the MIMNURF 360 dataset, speedy split with SafeguardGS improves PSNR and SSIM by 0.003 and 0.0025, respectively. On the tanks and temps dataset, POP3DJS with SafeguardGS achieves a 1.031 dB improvement in PSNR. In terms of qualitative comparison, our method produces sharper results and reduces blurriness after pruning. For instance, the stuff behind the bonsai has clearer boundaries in POP.SG, and the number of 713 on the train is more distinct in Light.js. The point visualization further supports that this improvement comes from plus pruning with our color-aware scoring function. For example, Light.SG retains points corresponding to number 713, where Light Gaussian removes them. In conclusion, we propose SafeguardGS based on the observation that blur pruning provides a safeguard property against catastrophic scene degradation. We also show that a scoring function combining color similarity and blending weight effectively maximizes per primitive expressiveness. Our experiments demonstrate that SafeguardGS performs well under extreme pruning conditions and can be broadly applied to state-of-the-art training pipelines. Thank you for listening to my presentation.